This video is going to discuss differential equations and just give a brief overview to differential equations. So just so we're on the same page, differential equation is a rate equation where we can express the derivative or possibly higher derivatives as a function in both x and y. So for example here, y prime, that's the first derivative of y, that may be a function that contains x and y. Okay, and just other notations that you might see, the equivalent form of this in Leibniz notation would be d of y of x over dx. Again, just saying the derivative of y, where y is a function of x, is equal to a function that contains at both x and y. Another even more common notation that you might see is this sort of thing. So this is saying that you have a function that contains x, y, and y prime equals 0. And this again would be, these are all examples of differential equations, specifically first order differential equations. Okay. So again, basic definition, differential equation, it involves a derivative. Okay. First order differential equations, which is going to be our main focus, are differential equations where the highest appearing derivative is the first derivative. So an example of that is, let's just say it's 8y prime is equal to 3x. Okay, that would be an example of a first order differential equation. Okay, if it so happens that the highest appearing derivative is a second derivative, then it's going to be a second order differential equation. Okay, an example of that might be, and these are actually fairly common, is if you have y double prime equal to let's say 4y. Okay, these are very common in physics applications. Okay, so again, that would be an example of a second order. Okay, some other examples that we might see, we could see y prime times 8 plus 3y plus 2x is equal to 0. Okay, again, all we need is something where at least one term of the equation has a derivative in there. Okay, and just to abstract away from x and y a little bit more, we could say 3p prime plus p is equal to x. Okay, that would be an example of a differential equation in p. We would assume that p is a function of x here. Okay, that would be a assumption. Some non-examples here might be something like e to 3t is equal to y. There's no derivatives in there. Okay, and if we have x is, let's say, to the third times y is equal to 2, again, there's no derivative in there. Those are non-examples. Okay, keep in mind, and I didn't do any examples here, but it could be the case that we have sine of, let's do m plus m prime is equal to e to the t. Okay, that would be another example of a differential equation. Again, as long as it involves a derivative, we're okay. Okay, now the other term that we want to get familiar with is what a solution is. Okay, so a solution would be something where would be a function, f of x, where if we substituted it in, okay, notice we substituted it in for the y and the y prime, we get out a true statement. Okay, so we have to substitute f in, and we may need to compute f prime. Okay, or f double prime. We may need to compute all these. We may need to compute the triple derivative. I don't know. But we need to substitute what we believe the solution is into the equation to see if we get a true statement as a result. So an example here, we want to test to see if this is a solution to the differential equation. Okay, and here's the differential equation down below. In looking at this, I see I have a y double prime, and I have a y prime, and I have a y. So that means if this is my solution, I'm going to need to plug in y right here. I'm going to need to plug in the derivative in here, so I need to compute the derivative, and I'll need to plug in the second derivative. So let's go ahead and compute those first. Okay, so we know y of x is equal to x to the minus 3 halves. And just for notation purposes, or simplicity I guess here, I'm actually just going to say y. Okay, we're going to know that it's a function of x. If I compute the derivative via the power rule, this is negative 3 halves x to the minus 5 halves. Okay, then again, so that would allow me to substitute in here. I need to compute the second derivative, so y double prime. This is equal to 15 over 4 after I do all the simplification. So I would bring the power down, multiply the fractions, x to the minus 7 halves. Okay, and at this point I'm ready to do the substitution. So let's go ahead and do that. So I have 4x squared, and then it says y double prime, but I actually have an expression containing x for y double prime, so I'm going to substitute that in. 15 over 4 x to the minus 7 halves plus 12x, and then it said y prime, so I'm going to go ahead and substitute that in. Y prime was minus 3 over 2 x to the minus 5 halves, and then plus 3 y was the same as x to the minus 3 halves. And I want to test to see if I get out 0. Okay, so I want to see if the left hand after all is said and done simplifies to something where I get 0. Let's go ahead and do the math. Okay, so simplifying here, 4's are going to cancel, and so my constant that I'm going to be left with is 15. Simplifying, so those would cancel. If I simplify the variables now, let's see, this would be the same as 4 halves, so I believe this is x to the minus 3 halves after I simplify the exponents. Simplifying constants here in the second term, so this is now plus 6 times minus 3 is minus 18. X, let's see, how does that simplify? So if I simplify those same bases, I would add the exponents. So this would be the same as 2 over 2. I get minus 3 halves. And then I get plus 3x to the minus 3 halves. So in total, I believe I get, okay, this would be 18x to minus 3 halves minus 18x to the minus 3 halves, which does equal 0. So my conclusion here would be, yes, y of x equals x to the minus 3 halves is a solution to the given differential equation. And again, just how do I know that? It is because I was able to verify that it was indeed equal to 0. That I got a true statement out. Okay. And then the last thing that we need to be aware of when we're solving differential equations is when we get a solution, when we actually determine the solution ourselves, some cases the solution might be given. But when we determine the solution ourselves, we could get two types of solutions. There's a general solution and a particular type of solution. These are very reminiscent of antiderivatives, and sometimes we had particular general antiderivatives, and then other cases we had specific antiderivatives. Okay, so a general solution, it's going to have an unknown constant in there. And this is essentially the constant of integration. So whatever we get from integration, that's going to be our constant. That's going to be our general solution. Okay. A particular solution requires a boundary value. Okay. So when we found specific antiderivatives, we use the language of initial condition or something like that. In solving differential equations, we actually have the language of boundary value. So a boundary value just means that we're given something that looks like this. Y of a number, so again this could be like y of 2 is equal to 5. Okay, where we just have some input for x and an output for y. If it happens that this input for x is 0, so it could look like y of 0 is equal to 3, that's when we're going to call this an initial value. Okay, so boundary value, initial value, just a little change in terminology. And that really is an introduction to differential equations.